you enjoyed coffee, enjoyed the poster session. So here we have the last invited talk of this morning. We have Anna Marasović on Zoom. So Anna is a faculty at University of Utah. Before that, she was a young investigator at LN2 and did her PhD at Heidelberg University. And Anna's research interests broadly lie in NLP, human-centered AI, and interpretability. So if you work on interpretability, scalability, you must have read Anna's papers. Very excited to have Anna. Without further ado, I will give the stage to Anna. Thank you.
Thank you so much for the introduction, and good afternoon, everyone. I really wish I could be there in the same room with you, but it is what it is. At least I get to speak to you remotely. Let's get into it. We gather here in this workshop because we want to talk about reasoning, right? And reasoning can refer to many things, as it's very often with a popular term in AI. But these days we are kind of taking this notion that that's referring to a skill that the model needs to have if the model can answer questions that involve complex processes with multiple intermediate reasoning steps. And we also implicitly want models to verbalize those intermediate steps to kind of show us their thinking process. And it's not surprising that this topic has become such a big topic in our field. It is foremost challenging, right? It kind of requires that we do multi-step processing that goes beyond the token by token autoregressive nature of large language models. It is foundational because it's a core aspect of planning and strategic decision making. And at the same time, it is promising since recent advances point to a viable path. And it all started in basically, by all, I mean, let me turn on my laser point. This kind of surge in recent popularity started in 2022 when it was noticed that if we add let's think step by step to our prompts, the models will start to verbalize their what seems like reasoning. And in doing so, we will also improve their performance on tasks that do require reasoning, like math. And since then, these verbalized thoughts have been often used as evidence of reasoning. However, we all know that what the model is showing us in a chat interface and what the model does internally does not need to necessarily match. So for example, here we have an example from Anthropic's recent blog work, where they show that a model that was prompted to solve this math problem is in its second step generating the digit 8, not because it has somewhere recorded what the cosine of this number is, or it has internally computed the algorithm for cosine, or have generated an action and had access to the external calculator. Rather, all it does, it has seen the decimal point here, and then it had somewhat randomly decided which of the possible digit could come next. So let me formulate a little bit this idea of what the faithful reasoning is. And this is going to be pretty informal, but I'm going to just state how in literature we often state what the faithful reasoning is. So we say there is some instruction, some question, and then there is some internal reasoning happening, which then it's displayed to us in our interface. And then given that whatever is displayed, there is more internal reasoning going on. And then again, this interplay between internal reasoning and what we are seeing on the display. And all of that together leads to the answer. And I should have said that this, whatever we are seeing on the display is an accurate communication of what's going on inside. On the other hand, unfaithful reasoning would be the one where we have an internally model doing something that leads to the answer. However, at the same time, we are seeing something as evidence of reasoning, which had nothing to do with the internal reasoning. Rather, It's kind of a model's justification of what would be a reasonable way to solve this task. As we have seen previously, the model had known that cosine should be involved in some way, and that's a reasonable justification, but it wasn't really the reason why the model had produced digit 8 in that place. So why is this a problem we're talking about? Why unfaithfulness of this verbal reasoning is something we should care about? I think it's obvious that if you see something displayed and that is not an accurate representation of what's going on, you are going to easily be misled. And we see that that's exactly what's happening. People are being misled by what they are seeing, and that causes things like them over-relying on these tools, thinking they're better than they actually are, right? If I see the model that can actually produce a right cosine of that number, I would deem it's way better in mathematical reasoning than it actually is. Domain experts in other domains, like legal professionals and clinicians, have said that they do want these verbalizations of reasoning to be accurate, such that they can do things they would like to do with these things. So us, AI community, by not producing these chain of thoughts that are actually faithful, we are not meeting the need of people in other domains. And similarly, if we had these verbalization being accurate representation of internal reasoning, we could do things like complying with the regulation. But something I want to point out to this audience who is thinking about how to design models that are capable of reasoning, I want to point out that even in our community, we are throwing ideas such as, oh, we can monitor our reasoning or large language models by looking at these traces. And by monitoring, looking at these traces, we can develop hypotheses of why they are wrong, and by wrong, I mean why they make mistake. And then based on that hypothesis, we can develop newer generation of these models. However, if these traces had nothing to do with what the model is actually doing, I would say that that would lead to very questionable way of developing these models. So my journey with this topic started already 5 years ago. Before 2022, we have worked on a type of explanations called free text or free form explanations, which are very alike chain of thoughts. And honestly, I don't think there is a substantive difference between the two when you're trying to both model them and test their faithfulness. And already in 2021, when he released what I believe the first study of trying to measure faithfulness of free text explanations, we have acknowledged that this is incredibly hard problem. And all we can do at that point is produce tests that we said these are the necessary tests for a faithful explanation to pass. However, it is not a full-fledged test of whether the explanation is faithful or not. So now, from my 5-year experience working on this, I can tell you this is incredibly hard topic. And for most, I think it's hard because if you want to say whether your verbalized reasoning is accurate representation of internals, today I believe that you do need to understand something about internals, which will be a big point about in my talk. Which means that you need to understand a complex system of high-dimensional dense vector that can do things like superposition, that can trigger their dimensions trigger for multiple things at the same time. And you also need to do that across multiple generation steps and kind of make sense of all of that, which is incredibly hard. And also, in some cases, even people struggle with to accurately report their own reasoning. And if you press us, we will make something up, right? So it's unclear what faithful reasoning in some cases should even look like. However, our field loves hard challenges, right? So I'm not going to stop my talk and say this is too hard. Let's go grab that lunch that awaits you in about 30 minutes. Rather, I will tell you how people have approached this problem measuring faithfulness of chain of thoughts in recent years. And I will try to present you an argument that we should do that somewhat differently. So the type of measurements we have been seeing in the recent years are of the type I call contextual or behavioral. faithfulness, where you're trying to change inputs and outputs and see you just change inputs and see how the model outputs change, and based on that, you want to say something about faithfulness of chain of thoughts. So one very popular example of that is that you generate chain of thought from your model, and you get some answer based on the chain of thought, and then you corrupt your original chain of thought in some way. So here, for example, we have dropped an important step. So that's called early answering. And in another case, we have added a mistake. Here, 5 factorial is now suddenly 100. And the idea is that if you have corrupted your chain of thought in some way, the answer should change as well if the original chain of thought had a big influence on the answer. Now, I think this is really hard to confirm that the change in the answer or the lack of the change comes from unfaithfulness. And I will try to visualize why I think that. My whole argument boils down that it's really hard to say what comes from internal parametric reasoning or knowledge and what comes from the context. So imagine we are working with this add mistake problem where we generate chain of thought and then we add a mistake. And then we add again to the model, we ask it, okay, solve this problem, but here is reasoning which is corrupted. Of course, we don't tell it it's corrupted. I can imagine that a skilled model sees reasoning that's flawed, and internally it reasons that there is a mistake, and it ignores the mistakes and defaults back to its original way of solving the problem using the proper reasoning that it had generated in the first place. Similarly, if you're truncating the reasoning and again give this incomplete reasoning to the model to solve the problem, I can imagine the model internally completes the reasoning and comes to the same answer. So this is more theoretical foundational problem I see with contextual faithfulness, but in practice we also have noticed stability issues. So in this work that I'm referring to here, they have shown that these measurement of faithfulness where you add or truncate the reasoning correlate highly by just measuring how much the model's prediction change with and without chain of thought. And what we have noticed is that this can suffer from position bias, right? So how much your answer change can, for smaller models that are not yet capable of doing this task, can happen just from, shuffling the order of your answer choices. So we tweak this measurement just by normalizing it with basically rate at which the model would change its answer only if we shuffle the answer choices. And what we have observed that previous results that shows that the smaller models are having quite unfaithful chain of thoughts, that observation changes and we see that their chain of thoughts are not as unfaithful as it was reported. If anything, the drop is massive here. And there isn't anything special about 13 billion models. They aren't the sweet spot of accuracy and chain of thought faithfulness. Another thing we notice here is that there seems to be correlation between unfaithfulness of chain of thoughts under this measurement and the accuracy with chain of thoughts. And we measure that, and indeed, when we use our normalized unfaithfulness, we see that the correlation between between normalized unfaithfulness and accuracy is massive. And to me, this has always been somewhat suspicious. For most, we never see such nice correlations in our field. But more foundationally, what this means is that with better performing model, which here I don't show you this plot, but you know that they are generally producing more plausible explanations or chain of thoughts, and although plausibility and faithfulness are not correlated, seems a bit suspicious that as the models get better and generate more plausible chain of thoughts, that those chain of thoughts are not the reason why the model improves its accuracy. So together these observations that it's really hard to distinguish what's going on internally and what internal influence is on the answer and what context influence on the answer is, together with some of these practical challenges, makes me say to you that to measure whether models internal reasoning and what it verbalizes match, we should look into its internals and not do this purely behaviorally. So this brings me to one of the two approaches I'm going to talk about today, about how we can measure the chain of thought fitness by looking at the model's internals. So this work is led by Martin Tutek. It's going to be presented at EMNLP, and I believe Jonathan had this morning already presented it at another workshop. Here you have QR code for the latest version of the paper, which is not yet available on arXiv. In this paper, we first present a general framework for how to measure parametric faithfulness, meaning faithfulness where that's measured by looking at the internals. And in this framework, we kind of embrace the notion that a verbalized reasoning step is faithful to the generated answer if this step reflects an actual internal mechanism, and which means that altering parameters that captures that step information should disrupt the model's ability to answer the original question. Specifically, we have a model that's instructed and generates chain of thought, and its chain of thought is our object of study. We break down this chain of thought into reasoning step. The granularity of that is upon the choice of the developer. In our work, we are going to take sentences. And then for each one of the reasoning step, we are, in this framework, we say you need to, in some way, alter your model such that its internal trace about information captured in that step is changed. And you should do only that change, such that you know later when you observe differences in answering or its reasoning content, you can prescribe it back to that change you have made. Which means you need a control that ensures that your intervention on parameters was targeted in that way. Once you confirm with your controls that yes, indeed, you have done exactly what you intended to do, then you can see what the answer from this modified version of the model is and check whether it changes, which it should if the original reasoning step was indeed crucial for the internal reasoning of the model. So I'm going to first talk about how we realize this parameter intervention with unlearning, and then we are going to see what the faithfulness results are. So the goal is to, again, disrupt, change the internal trace of a reasoning step in a model. And the intervention we are going to choose is unlearning. So we are going to effectively eliminate the influence of specific unlearning targets and remove associated model capabilities while preserving model performance for some non-targets. And our controls will basically be measurements people use for unlearning, which are efficacy, checking that you have indeed unlearned what you had set to unlearn, while also retaining general capabilities and performance on a held out set. Now, there are many, many ways you can go ahead to do unlearning. In this specific work, we are focusing on the upper left part of this set of possibilities. And specifically here, we are looking into approaches where we are going to fine-tune the model to unlearn what we said it to unlearn while retaining knowledge about the set of things we said it should remember. And this line of work is building on this idea that to unlearn something, basically you need to reverse training. And training means making a gradient descent step. So by doing gradient ascent step, you're basically canceling out what you have done. However, a work that has been published in Column last year, has shown that this can lead to a rapid deterioration of the performance on the held out data because this method converges too fast. And what they did is they proposed another way to train a model to forget information that doesn't cause this catastrophic collapse. Specifically, their method called negative preference optimization basically takes our favorite optimization objective for preference training, DPO. It assumes there is only a losing response. So if you cancel out the term that is connected to the winning response in DPO, basically you get NPO. And they show that this version of NPO for unlearning is converging slower than the gradient descent. So this is how we basically forget information. We give some, prompt and or completion so far, and there is some target, and we want to forget that token could be a reasonable next token, and to do that, we are changing parameter using this objective. On the other hand, we need to remember our retain set, which we do with the KL divergence between the current model we are training and the reference model, the model we begin with. Okay, so that's going to be our objective, MPO with the scale divergence. And how specifically we use it is like this. So we have our problem, we have chain of thoughts. We are going to assume that every sentence of the chain of thought is a reasoning step. And then we are going to define our forget set as a set of all content words. That's going to be basically what instantiates I in the previous equation. So given everything that had preceded a content word, we are trying to forget that the content word that actually had appeared in the step could be the next token to generate. So these tuples here I'm showing, these are basically our xi pairs in the forget set that we are going to use with the NPO equation. And we are similarly going to create our retain set, which is going to contain content word completions from 4 randomly chosen other steps. A few more details. We are not going to change every single parameter in our transformer. Rather, we are going to target the second, fifth order matrices because these have been shown to act as a memory store. And it's very often they are chosen as editing targets. We are going to unlearn for 5 iterations, each set steps separately. And 1 iteration of learning means unlearning all of the content words in that step. And we have seen that learning grade selection has been hugely important for us. So now let's see first our controls. Is the target information removed is the first question. And to measure that, we are going to use the efficacy of unlearning a reasoning step to be the reduction in the length normalized sequence probability of the unlearned CoT step. So basically we'd see what its probability of the step before we do unlearning and how much it reduces once we unlearn that step. And here I want to emphasize that we do want to see reduction, but we don't want to see a total reduction of 100%, because that would mean that the probability of a reasoning step after unlearning is 0, which would mean that the model doesn't deem that sentence, which is grammatical fluent sentence in English language, to be fluent anymore, which would likely lead to the deterioration of its general capabilities, which we do not want. So here, it is really hard to say what the ideal outcome is, but what I want you to notice is that there is a notable reduction, right? We see rates that range from 20s to 70% reduction of these probabilities. So unlearning of these targets is definitely happening. As I said, we don't just want to learn things and break the model, we want to keep its capabilities. So here we are seeing how much the model after unlearning agrees on the answer for some held out retained set with the original model before unlearning. And we see here generally rates that are in higher 90s, which means that after unlearning, the model is in a high agreement with its original version for these held out data. And similarly, for general capabilities, here we see performance of these models on a subset of MMLU and Big Bench, and we see that the performances after unlearning kind of stay about the same. So that's good. That means that we have done the intervention we wanted. We wanted to unlearn just the reasoning step, and these controls suggest we have done that. So now we are in a position to see what the faithfulness of our chain of thoughts or reasoning steps is. So we are going to define two measurements. First one is going to check, does unlearning any step causes the model to answer differently? And if that happens, then we say that the entirety of the chain is faithful. The idea here is, although some steps might be faithful and others not, if there is a faithful step, then the gist of the reasoning is there. On a different metric we propose here is to also see how much probability mass has a learning step shifted from initial answer. And this measurement tells us which are the most salient steps of the reasoning chain. But today I'm going to talk about this FF hard, and there's a bunch of additional results in the paper. So the problem with evaluating metrics for chain of thought faithfulness is that there is no ground truth. If there was ground truth, that would mean that interpretability is solved. So the best we can do here is to see whether our values that we get with our faithfulness metric differ from some other work. So here we look at that add mistake work I have shown you before, and what we do notice is that there is a big difference in the faithfulness value. And most notably, it seems that the values of faithfulness we get are higher from this add mistake, which suggests that it might be underestimating chain of thought faithfulness. Okay, so this is all I want to say about the unlearning-based approach to measuring parametric faithfulness. There are way more results and experiments in the paper, so please check it out. But I want to switch gears and talk about another ongoing approach for measuring parametric faithfulness, which I emphasize is very ongoing. So I will show you just very preliminary results here. But basically, I want to go back to this idea that we can generate this chain of thoughts, and then we have some kind of subgraph that tells us what is happening internally. This is really sweet because it tells us precisely why a crucial step like this one was generated with this subgraph. So it kind of seems that the problem can boil down to checking if this internal subgraph and what is verbalized is matching, which is feasible. You basically have two things and you need to figure out how to match them. I'm not saying it's straightforward and easy, but it's more feasible and tangible than if you don't have those two objects. Also, what it enables us is understanding exactly how a step is unfaithful to internal reasoning, which we can illuminate what kind of unfaithfulness can happen. So previously we had a case of what anthropic folks calling bullshitting, just making things up, saying that, I'm using a calculator to get the cosine when in reality there is just a random sampling of digit happening. Here there is something a little bit more interesting going on. Here a user says, oh, I think the answer is 4. And because this problem has 5 by cosine, the model is producing digit 8 here by dividing 4 by 5. And this is a case of so-called backward or motivated reasoning. So by looking into these subgraphs and how they match chain of thoughts, you can get information about how specifically the step is unfaithful. This is all very nice, but the problem is that this kind of vignettes, this like subgraphs that kind of capture the gist of what's going on, were made manually by top experts in Anthropic. So for most that takes time, right, and limits how we can do this at scale. I don't know what the salary anthropic is, but I suppose an hourly rate of top experts there isn't cheap, so that costs a lot of money as well. And also, we are risking confirmation bias when we do these things manually. So a big question here, I think this approach of trying to match these subgraphs with the chain of thoughts to measure their faithfulness is a great way to go about things, but a big issue is how we can automatically discover these, what I call extremely sparse feature circuits. And to tell you how Fatem and I are going about this, I will need to give you some background. I also want to give a shout out to Martian folks who have generously funded us to do this work, which is highly appreciated at these times. But going back to the background to be able to tell you what we are doing here. So the first thing we need to do is produce an interpretable version of our MLP outputs in our transformer. You know probably that we don't generally want to inspect the MLP activations directly because their dimensions can trigger for multiple unrelated concepts, which we call polysemantic neurons, or we say that these things are in superposition. So the field of mechanistic interpretability has tried to decompose these activations and reconstruct them as a weighted sum of feature directions, where these feature directions are learned and they are stored as columns of the decoder weight matrix. So basically, when you do a dot product between these matrix and this vector that stores the weights of each latent feature, you get the reconstruction. The way that we get how much latent feature matters for a given input is by doing a product between the encoder weight matrix, whose rows corresponds to these latent feature directions, and the input to the MLP. So basically, to say how much the first latent feature is important, you take the first row of your encoder matrix and you do the dot product with the input to MLP. Importantly, most of these values here are going to be 0 because that enables interpretability, right? So although you have 100,000 features, you are going to maybe keep only 200 active here. And just quickly, cross-layer transcoders are basically extension of this idea where instead of having one of these products, we have multiple of them. Basically, if we are given layer L, we have as many of those as there are layers under L. And instead of reconstructing with one of these matrices, matrix vector products, we reconstruct with the sum of multiple of such products. Okay, quickly a little bit more about the background. So far, we have learned these weighted sum of feature directions to decompose and reconstruct our original output. We do need to assign the meaning to these dimensions to be able to say like what then is encoded in this representation. And to do that, we pass a large corpus to this transcoder. We check for which tokens the values in this vector are really high. And then I should say not all values. If we are going to assign the meaning to the first dimension of this vector, we will check for which tokens the first dimension here contains high values. We will get a set of such tokens, and then we would use an LLM to generate pattern among them, such as court references and legal terminology here. And then what's important with transcoders is because if you ignore attention for a moment, you're basically, your output of your MLP is input to the next MLP and so on. And now if we are reconstructing each one of the MLP outputs with these products that involve weight matrices of the decoder and encoder, then through these weights, you can see how much one feature in one layer is impacting another feature in a higher layer. And specifically in the work that had proposed transcoder, they do it by taking the dot product between the earlier features decoder vector and the later features encoder vector and scale it by the latent activation of the earlier feature. So now what you have are all these features. For example, here I clicked on a feature direction that has been described by some LLM as feature Texas. And you also have how much other lower feature impact that feature and how much that feature is impacting higher feature. And importantly here, you put all of this into a graph where these nodes in a graph represent features and edges between them represent these influences. However, this graph is going to be large. It's going to contain thousands of nodes, lots of edges, and so on. So the goal here is to find a more pruned version of that, which is also referred to as sparse feature circuit. However, even when we do all this pruning, it has been reported that these pruned graphs are still quite information dense. They contain hundreds of nodes and tens of thousands of edges. So to produce this nice biology of LLMs analysis, Anthropic folks had to do this manually to digest these prune graphs into something smaller and compact, such as, for example, this subgraph over here. So you take your prune graph, see these values indicates there is pruning going on, but you still are selecting something smaller within it. And there is also, importantly here, supernodes, which are groups of features that are best deemed to be looked at as a functional unit in analysis rather than isolated features, which makes additional layer of complication. So just to kind of zoom out and tell you why I'm telling you all of this is because we do want to produce these vignettes, these extremely sparse feature circuits, because then we can quickly see whether they match with the chain of thoughts. And I told you the problem is that so far we have been doing this manually, right? So this brings me to what we are trying to do. So what Fatima and I are noticing is that these vignettes resemble somewhat skeletal graphs, right? So here you see this is a let's say imagine this is an input graph. The field of graphs skeletonization is trying to find this minimal backbone that preserves its essential structure and function, such as preserving the information that there is a large cycle here and that there are two components attached to the bottom. So this kind of made us think, well, can't we just then approach finding these vignettes by applying graph skeletonization methods to attribution graphs? Specifically, we are using a method from topological data analysis called mapper-on-graph, with which you define some lens, some way of looking at the graph, and depending on what the property of that view is, you are going to get different skeletonization of that graph. And this lens is just a function that goes from the set of nodes and assigns each node a scalar value. Then you can take the interval minimum and max values of that function, that topological lens, and you can partition it in equally sized intervals. And then you can say, well, I will assign to each one of these original nodes which interval it belongs to. Once you do that, you can say all the nodes that belong in the same interval are going to be one node in a final skeletonization, or you can do additional clustering. And you assign an edge weight based on how many edges there are between nodes in different components of your topology. So we are applying this approach to this problem of finding the compact subgraphs in attribution graph. And two lenses we are going to choose, there are two of them. The first one is to assign a score to each node that reflects how much it contributes to the final output through the most impactful routes, rather than all possible paths, which we found that doesn't work really well. So basically, imagine you are here and you can find which input features has positive influence on this node. You normalize their scores between 0 and 1 and make them sum to 1. And then similarly, like we do beam search, you multiply each normalized scores with the score of each n of the n stored paths. And then you keep only the top n extended paths, and this becomes your beam. And then you repeat for each one of these top surviving nodes that influence the current nodes, and so on. For other lens we are choosing is the one that was going to help us create supernodes. So here we take the label description assigned to a feature like Texas, we embed it with BERT embeddings, and we then just applied 1D PCA to these embeddings, and basically now all descriptions are going to be assigned to some interval. And to show you how this visually works, imagine this is your attribution graph. We apply our impact lens, and by doing what I told you to do, we are going to get some top and paths and nodes that correspond to these most influential paths to the output are going to be the one we keep here. And there is going to be some topology here that's happening, but we basically are currently ignoring it. And we apply supernode lens, which then groups surviving nodes based on whether they should be seen as a functional unit or not. Okay, I know I'm running out of time, so I'm going to wrap up. I'm going to just show you what happens when we apply this to one example in Neuropedia. So here you have a prompt, fact colon, the capital of the state containing Dallas is, and the output, the most likely token is Austin. This is the attribution graph, and manually you can select a subgraph, which is a plausible way to solve this problem. So going from capital state and Dallas, you are connecting to Texas, and you also have state capital, so that together should lead to Austin. This one has been manually found in the attribution graph. When we apply our method, we get something kind of similar on a good track, right? Again, from Dallas, we have Texas. And although it doesn't seem like we have a lot of cities, but not really, say, capital, when you zoom in, you will see that here, downtown of city capital is a very, very highly active token. And here, one of the feature is going to be quite influential for outputting capitals. And in a manual subgraph, this has been manually changed to say a capital. So we are actually capturing those important feature for plausible reasoning here automatically, while these scores are almost the same. And we find a similar thing for the same example, but for the haiku model rather than Gemma 2 billion. So this is a manual feature. And then when we apply our methodology, we again have Dallas, Texas, say Austin, and capital, importantly, that before say Austin, that leads to Austin. So although this is very, very preliminary, I think it's quite exciting that we are getting this extraction of these extremely sparse feature circuit automatically, at least for these examples. And of course, it remains to be seen whether this holds at scale. So stay tuned next time I give a version of this talk. Thank you so much. I'm sorry I took some extra time.
We're a little over time, but we still have time for 1-2 quick questions. Jump ahead. Well, I guess people are in your rush to go for lunch. Let's give our speaker a round of applause again. Thanks, everyone. And I hope to see you again in the afternoon. Thanks, Anna. Thank you so much.
Thank you so much. Have a good rest of the workshop.
Oh, or laptop.